Distinguished Academy members, esteemed colleagues, thank you for allowing me to be present in this extremely stimulating meeting. And I'm especially grateful to Brother Guy for thinking that presentation on Rubin Observatory could be interesting to this audience. So Rubin construction is about to be completed in Chile. We'll start next year with the first science project, 10-year-long survey of the sky called Legacy Survey of Space and Time, which will obtain the largest ever astronomy data set and probably one of the largest scientific data sets ever. About 60 petabytes of data will be collected. And not only it's going to be the largest data set in astronomy, it will be more data than all the data that astronomers collected since Ptolemy. So what does it have to do with this conference? What is the connection to Anthropocene? This is an iconic image of our planet. From the moon, it looks like we haven't done any damage to it, which is good. This is another iconic image from 6 billion kilometers away by the Voyager. You see this tiny dot, compared to the rest of the universe, it's really tiny. So the first conclusion is that the universe doesn't care about what we do. We are so tiny and insignificant that universe is doing its own thing. I will have to quickly qualify this. Just 2 years ago, there was a spacecraft that had collision with a moonlet of a binary asteroid and changed its orbit. I think philosophical implications of that are equal to moon landing. We managed to change orbit of a celestial body. It's scary, but it's not topic of my talk today. So the universe doesn't care about what we do, but we care about what the universe is doing. And this is why we are building Rubin Observatory. There is no direct connection to issues like when exactly Anthropocene started, what bad things we did to our planet so far. And the connection is with AI, and I'll get back to that at the end. I want to first tell you a few words about motivation for this large sky survey, which resulted in community and federal support for Rubin Observatory. It's about a $1.5 billion project funded by National Science Foundation and Department of Energy with significant international collaboration. We have over 2,000 scientists organized in science collaborations from about 40 countries around the world. Then I'll tell you a little bit about what AI or machine learning or big data what role it will play in Rubin and LSST. And I hope to have a few minutes at the end to talk about one of the dangers for our success that comes from our impact on environment on low Earth orbits, where there are thousands of satellites already. We think it will be 50,000 satellites within a few years, but if you look at requests for permission to launch to federal regulatory agency, it could be well over 1 million satellites. And we have no idea what's carrying capacity of low Earth orbits. So it's something that requires legislation. So modern astronomy today addresses 2 questions: search for life elsewhere, and David just gave a beautiful talk about it. And the other big question is understanding the universe. We've known for 100 years that the universe is expanding since Edwin Hubble, and we expected that expansion to slow down because the only relevant force is gravity. We didn't know if it would expand forever or come to a halt and then collapse back, but we expected that the expansion has to slow down. It was a huge surprise 2 decades ago that the universe is actually accelerating. The expansion of the universe is accelerating, and we have no idea what is the physical cause. There are 2 ways to explain it. One is to postulate some new major constituent of universe that accounts for about 70% of energy mass of the universe that we call dark energy, and we know nothing about it. Or when we derive this conclusion that we need another term in equations, we start by assuming general theory of relativity that describes gravity is correct. But it could as well be wrong. Maybe Einstein was wrong. Maybe we need to modify that theory, just like Einstein modified Newtonian gravity. We don't know which of these 2 possibilities is less wrong. And in order to start distinguishing their predictions, we need better astronomical data. And here, by data, I mean very precise measurements of galaxies. We need billions of galaxies based on simulations of when you say, what do these possibilities predict? In order to get statistical significance in their differences, you need billions of galaxies. Here is an example of what we know today. So we are in the center, and we want to measure distribution of galaxies like shown here. Each little dot, there are about 100,000 dots, is an individual galaxy from Sloan Digital Sky Survey. You can see that there is structure in that distribution. It's not random. And that structure encodes physical parameters that govern expansion of the universe and growth of structure. Simulations show that in order to distinguish these possibilities of GR being wrong from existence of dark energy, we need to extend our reach. We need to see further to get 20 billion galaxies. So we need to have bigger telescope, and we need to cover significant fraction of the sky to get to 20 billion galaxies count. And telescopes that could do sensitive observations that are required today could do the job, but it would take about 1,000 years for them. Or if you take all 10 big telescopes that we have as humanity, it would take 100 years. So that motivates construction of a completely new observing system. There are other science pillars that I will not go into detail. They are based on opening time domain for faint objects. So if you calculate over 10 years, it's about 8 hours of exposure time per position on the sky. We are not going to get one long exposure of 8 hours. We are going to split it into about 1,000 exposures over 10 years, which will allow us to look what's changing on the sky, what's moving on the sky. Like, for example, asteroids. We will be very sensitive to potentially hazardous asteroids. In the lower right, you can see a beautiful crater from Arizona where there was an asteroid impact about 50,000 years ago. So we will be able to get census of objects that are larger than about 140 meters, which is limit below which tsunamis do not kill a lot of people. So what kind of data are we getting? This is example of one of state-of-the-art surveys today. First digital sky survey, Sloan Digital Sky Survey. It's about 1/10 of the full moon's diameter across this image. What we want to do with LSST is to become more sensitive. We want to get this image. So this image is real data. It's from the Japanese Subaru telescope in Hawaii. And they can do the sensitivity. They cannot do the whole sky. So we want to go from this quality to this quality and extend it over the whole sky. And it's amazing how much more detail you get when you're more sensitive. Whenever I get super tired of my Zoom meetings and I lose motivation, I go to these two slides, flip back and forth, and then I'm happy again. So the technological secret to getting this huge sample of galaxies is a very large field of view, telescope designed to give you a large field of view, as well as a camera that will have enough pixels. We'll have 3,200 megapixels in this camera, over 200 CCDs, that will enable us to scan the sky fast, because the field of view, each image, is 100 times bigger than typical field of view. We will be doing it 100 times faster. We'll finish the job in 10 years instead of 1,000 years. So it took us 20 years to go from the initial conception to being on sky in a few months, and we had to develop a lot of technology. LSST camera is the largest astronomical camera ever constructed. Simoni Survey Telescope is a very agile telescope, faster than any other one of that size, and we have a very complex data system, few million lines of code, and very complex algorithms to process the data. This is image of the telescope while it was still in Spain. A company from Spain constructed it following design from the US. It has 5-second slew and settle time, draws 1 megawatt of power to go from one point to the other. It's an amazing machine. The camera was completed just half a year ago at SLAC laboratory in California. This is the camera going for the last round of testing. This is the entrance lens. You probably learned in kindergarten that the largest lens was at Yerkes Observatory, close to Chicago, the refractor, 1-point-something meters. This one is now the largest lens ever produced. It's the entrance lens for the camera. So let me conclude this part about Rubin just by comparing it to some other great observatories being built. James W. Webb Space Telescope is already flying, and you'll hear more about it today. It's an amazing instrument. It's successor to Hubble. It's better than Hubble because it has larger mirror, 6.5 meters versus 2.5, and it's more sensitive, etc., but it's bigger mirror. Nancy Grace Roman Space Telescope will be launched in a few years. It's also a success to Hubble. It has exactly the same mirror as Hubble, more or less, but it has 100 times larger field of view. So for every 100 images that Hubble would make, Nancy Grace Roman Telescope will just do one image. And then on the ground, we have these 4 telescopes. On the left is the largest telescope that will be being built in Chile, led by European community, European Southern Observatory. If you want to learn more about it, a person who was most instrumental in bringing it to reality is sitting with us here, significant other of our co-chair, hiding in the corner, my old friend and colleague, Tim Dezu. So you can ask him during coffee break about this telescope. It is the largest telescope in the world. The 2 in the middle are US-led. We are still struggling to get federal funding to complete the financial background. So Rubin looks teeny tiny on this image, but when you look at the data rate, it's by far the most powerful telescope on this slide. It's named after Vera Rubin. She was an astronomer who provided first firm evidence for dark matter. She's also famous for advocating for women in science. She was the first woman who observed at Caltech's Palomar Observatory. So what we want to do with this observatory is quite simple. We want to have a machine that can scan the whole sky every 3-4 nights. We cover the whole observable sky, and we do it over and over and over for 10 years. So in 10 years, we'll get about 1,000 observations of each point across half sky visible from Chile. That's why the title of my talk was the greatest movie of all time. If you now stitch this with 30 frames per second, adjust it to the resolution of the human eye, it would take you 12 months to look at every single pixel with 30 frames per second without sleeping. Altogether, it will be of the order 100 petabyte data set, and it will include measurements for 40 billion objects. It will be the first time in history that astronomers will have cataloged more objects than living people on Earth. So literally, we can name a star and a galaxy after each and every one of you. So what do we do with AI and machine learning? I'm not distinguishing precisely AI, machine learning, big data, because I don't think these definitions are firm. Some people will call machine learning as AI. Some other people will say it's not AI unless it's AGI. So I'm not going to go into the discussion. I'll just show some of the exquisite software, ML-driven, that we are using in observatory. So the observatory itself, everything except making coffee is controlled by software, and we are working on that one too. The scheduler is a piece of software that decides where you're going to point next, and we need to make 2 million such decisions, so it has to be driven by software. And then I'll tell you a little bit about science analysis. Too many words on this slide, but the gist of it is we need to decide over 10 years, about 2.5 million times, where is the next field on the sky, how long we are going to expose, and what filter we are going to use. We'll have 6 filters in the camera. And then you have to look at observing conditions, which we are measuring in real time, and basically it's cost-benefit optimization. And it's way too complicated to do it by humans. We are not going to have humans decide. It's an algorithm, and we already have it implemented. This is simulation, but it's exactly the same code that will be running the telescope. So this is 1,000 times faster. This jump is about 40 seconds long in real time. It will optimize for observing conditions. There is metric that is benefit. It will think about future regrets, like if you paint yourself in the corner, et cetera. That's what's going to drive the telescope. It will be one data set that is optimized for all the science that we are going to do, all our 4 science pillars. And it's possible to do so because the telescope and the camera were designed to enable this. And so that brings us to this new way of doing astronomy. When I was a grad student, you could be observer or theoretician. But today, you can be data scientist and be an astronomer. You can do great astronomy without ever visiting a telescope. There will be database with about 1,000 measurements for 40 billion objects that you will analyze to get some science. And so when you look up at astronomy that we want to do and you translate that to language of computer science, of machine learning, then you realize it's like the bread and butter machine learning. We want to characterize objects. We want to discover these morphologies in the multi-parameter space. We want to classify new populations. We want to look for unusual objects that usually are very interesting in astronomical context. So we are doing that today. The only difference is that we will have 10,000 dimensional space populated by 40 billion points. And so obviously you can't load this data in Excel spreadsheet and do something with it. You have to design new algorithms. Polynomial algorithms like n squared, n cubed, they won't work, and people are working very actively into taking the most important algorithms and trying to come up with n log n solutions. And there is a lot of progress. When people are pressed hard that they need to do something, they come up with solutions. So let me just say a few words at the end about low Earth orbit satellites. Over the next few years, SpaceX and other providers launch thousands. When you plot, I don't have graph here, when you plot the number of satellites in LEO orbits versus time, it's a hockey stick, just like what we saw in this conference. Elon Musk and buddies, are having major effects on our environment, not just our 2D environment on Earth. Now we are going to 3D. We are destroying, it's still not catastrophic, but we are moving in the direction of destroying the night sky, not only for professional astronomy, but for us as humans. If you want to look at night sky, you don't want to have hundreds of bright objects that are brighter than brightest star moving across the sky, and it's still totally unregulated. So to have quantitative predictions, you need to know how many satellites you'll have, how bright they are. We did establish collaboration with SpaceX. They did try to minimize the brightness of their satellites. At the beginning, they didn't even care. They didn't even know it mattered. Then they were nice. I have to say they were nice enough to talk to us. We gave them advice what should be done. They found technological solutions, but it's like you go 2 steps forward, 1 step back, because they want ever bigger satellites, more bandwidth, and so it's not converging. When we do all these calculations, at this moment for us, Rubin Observatory, it will be a major nuisance. We will lose about 1% of pixels. If you translate to money, it's maybe $15 million. It's not a big deal, but if they continue on the trajectory they have right now, before the survey is over, maybe it will be 90% of pixels, and we don't know yet. So we think we made good progress with them in collaborative engagement, but we also need legislation. They will not stop without some further legislation, and you can see this is even, these SpaceX LEO satellites, they're smaller than this table in the middle, but if you look at this one, that's huge, and that would be brighter than 0th magnitude star. It would be brighter than any star on the sky. So it is a concern that we have in astronomy. So I'll stop here. I would be happy to entertain questions. Unfortunately, after questions are over, I'll have to run away because of my flight, but this conference was fantastic. Thank you all.